everybody. This is just a podcast looking at conservation of energy, and in particular, how we can get dynamic information from conservation of energy. So in class previously, we've looked at things like given an initial condition, what's the speed after a certain time, or what's the height after a certain time, but can we actually get time-dependent quantities from conservation of energy? So the question we're looking at the moment is the following. So use conservation of energy to find how position changes with time for a particle released from rest at coordinate y equals h, subject to a force F equals minus mg, and that's in the y direction. So this is a familiar kind of problem, concept force problem. We're just using a familiar setup in order to demonstrate this idea. We could have gone for a more complicated problem, but this is just so that we can understand what's going on. Okay, so first of all, it specifically says use conservation of energy, so we better do that. So we know that energy comes in two forms. So energy is kinetic plus potential energy, and we know that kinetic energy is a half m times velocity squared, so we need to find out what potential energy is, and we know that F is minus grad V is an equation we can use in order to find the relationship between potential and force. Okay, so well, F is minus mg like that, so we've seen this in class already, but if I'm just going to go straight to the to an ansatz, which will turn out to be correct. If we say that the potential is mgy plus some constant v0, then you can see that if we take minus grad of this, so minus grad v, it's going to be minus dv by dy in the y direction, because there is nothing happening in the x or the z direction, so you could include them if you wanted to, but we're just going to set them equal to 0. If we do that, then we can see that we get exactly minus mg ey, and that's exactly what the force is here. So we're getting it there, and this should be equal to the force, and this is correct. So therefore, we're going to use this equation here as our potential energy. Okay, so then we can proceed, and we can say, well, energy is conserved here because it's a conservative force, because the curl of F is 0, so I can even write it down. Curl of F is 0, therefore conservative force, and energy conserved. So E conserved. And we're still going to use the same idea of conserved quantities to look at a quantity which is constant, and equate some initial conditions to some conditions at a later time. So here, what we're told is that so particle is released from rest at y equals h. So we know that at time t equals 0, it's released from rest, so t is 0. Kinetic energy gets not moving, and then potential energy is just going to be, well, we're going to use this formula mgy, but y is h, and then we can include this constant. This constant is not going to make any difference. It's going to occur on both sides of the equation, and it's going to cancel. But let's include it anyway, just for completeness. Okay, so then we know what the energy is at time t, and the energy at time. Sorry, we know what the energy is at the initial time. Energy at time t is just going to be a half m times mod r dot squared plus v. But this is essentially a one-dimensional problem. Only things are only moving in the y direction, so this is a half m y dot squared plus, and we can put this straight in here, mgy plus v0. So this is energy at time t. Now, because energy is conserved, we know that energy at time t equals 0 is the same as energy at any time t. That's what being conserved means. So we're just going to equate our initial energy and our energy at time t to get an equation. So energy at time t equals 0 is just mgh plus v0, and energy at time t, which is written down as a half m y dot squared plus mgy plus v0. And as promised, the v0s cancel on both sides, so we can get rid of those. And we also can cancel a factor of m on all of these things here. So we're left with the equation that, let's bring everything over to this side, g h minus y, 2 here as well, is equal to y dot squared. Now I'm going to write y dot as dy by dt, and that's all going to be squared like that. Okay, so why have I done this? Well, that's because y dot gives the differential equation, and the question's asking us how to find out how position changes with time. So there we go. We want somewhere in here to find a time-dependent quantity, and the only time-dependent quantity I can see is, well, where the time variable occurs, they're all time-dependent, this is a time-dependent quantity as well, is in y dot. So if we write it like this, then we can see, okay, this is a differential equation, it's an ODE, we know how to solve this. If we square root both sides, then we're going to get that plus or minus square root of 2g h minus y is going to be dy by dt. And this is the first order ODE. It's a separable ODE. You know how to solve this from the second year course. And so we're just going to multiply across. So this becomes plus or minus the integral of dt. We're starting time at 0, and we're going to time t, is equal to the integral dy over square root of 2g h minus y. And so you might ask yourself the question, how do you do this integral? The integral on the left-hand side, of course, is quite straightforward. The one on the right-hand side, well, we can do it, turns out, by reverse differentiation. We've got basically a linear power under a square root, and if we make the observation that if we do dy dy of h minus y to the power 1/2, then this is just going to become 1/2 times minus 1 because of the minus y, h minus y to the minus 1/2. And so just rearranging this and integrating, that basically says that 2 minus 2 times square root of h minus y is equal to the integral of root h minus y. And that's what we have here. We're just multiplying by this this factor. It's just a constant which we can take outside the integral. All right, so putting all that together, the left-hand side of this equation then just becomes plus or minus t. And the right-hand side is going to become, well, let's take that 1 over root 2g outside. Then use the result that we have here, namely the left-hand side. And then we get a minus 2, trying to do 2. And then a square root of h minus y. And the square root of h minus y is, remember, we've got some integration limits here between h and y. Okay, so just evaluating those integration limits and simplifying the numerical factor. So it's going to become plus or minus root g over 2t is equal to minus, and then it's going to be root h minus y. The lower limit, when we put it into there, is just going to give us 0, so that we just need to evaluate the upper limit, and this is what we get, which is an equation which is relating time and position. And you notice that we've got a plus or minus here. Why do we have a plus or minus? Clearly, we only have one time. Well, one of the reasons is because at this point, this is where we got the plus or minus from. We've not said whether dy by dt is positive or negative. Now, it's released from rest, so, and the force is downwards, so therefore y dot must be less than 0. If it's less than 0, then we definitely take the negative root. So if we do that, then following that consistently through, this becomes a negative, this becomes a negative, and the negatives on the left and right cancel, and we get time which is positive. So that's all nice and consistent. You might ask yourself, well, what if we're taking a positive root instead? What does that mean? Well, we didn't say where, we want anything about time, whether it's positive or negative. So if we'd taken the negative route, then we would have been implying that maybe in a previous time, so negative time, the particle was released, given some velocity, and ended up at a height h a bit later. So that's what we would have got out of that. Anyway, so we take a negative route, and then in the end we get something that's positive. But in the end, it doesn't actually make any difference, because what does the question ask us? The question asks us here asks us to work out the position, how the position changes with time. Okay, so we just want to rearrange this now for position. And the first thing we're going to do is square both sides. And when we square, the plus or minus question disappears anyway. We get h minus y on the right-hand side. And then just rearranging this, we get y is h minus gt squared over 2. Okay, this is a really straightforward example, so the result makes perfect sense. But obviously, we want to make sure that our methods are consistent, so that in unfamiliar territory, we also get things which are correct. Those of you who did A-level maths, there's S is a Suvat equation, ut plus at squared over 2. Here the acceleration is minus g, so that's this term. And then S is displacement, and so the displacement is y minus h. And it's negative, so in this case, and that relates it to one of the Suvat equations. So this is a really straightforward example. This is how we can get temporal information from conservation of energy. What do we do? Let's just review very quickly. We use the fact that energy is conserved because it's a conservative force. So this step, because energy is conserved, energy at initial time is equal to energy at just a general time. So we equate these two sides together, and we get an equation which relates the speed to the position and acceleration. And we can write this as an ODE, and we can solve this ODE just using methods from the second year. And when we did that, we got an equation which relates time to displacement as well as acceleration, and rearranging that we got how coordinate depends on time. So this is essentially the trajectory in one dimension. If it was a multi-dimensional problem, then it'd be more complicated, and maybe we'd only get the modulus of certain quantities rather than the full trajectory information. But this is kind of a neat way how you get temporal information from conservation of energy.